Okay, so here's where we were last time. We said that the one loop effective action is finite. I won't keep on qualifying what I mean by the word finite, you know. If we use the usual classical action in the path interval, we use this in the path interval, or corresponding Hamiltonian bicanonical methods. If we use this action plus, or if you want, minus the local divergence action, for kind of a dumb reason. This is something that gives us divergences at one loop. If you use this, if you just start writing a local action and you plug it in, you'll get one loop divergences typically. But the one loop divergences will be local, meaning they'll have this form. And every term in this one loop effective action and the one loop divergences will be order h bar suppressed with respect to their counterparts here. Okay, so for example, this thing might contain a phi to the fourth, a lambda phi to the fourth. This thing, by doing graphs of this type and looking at the local divergence, might contain terms, again, in the effective action, might contain terms that look like lambda squared, phi to the fourth. Okay, so there's some, we're going to do this, but we're already expecting a local divergence, so here's a local counter term, here's a local structure, phi to the fourth x, with no derivatives, say. It looks just like this, except it's suppressed by an extra lambda. But the extra lambda is order h bar in our way of counting. Because lambda, for phi to the fourth field theory, lambda is the loop counting parameter, which is the secret of what I mean by h bar. So that's why we wrote the action in a form where lambda and h bar appear in the same place in the path interval, so that we can say it quick. Even if I have 10 couplings, I showed you how to sort of extract a sort of common coupling called xc, where the xc goes with the h bar, and so, or xc squared goes with the h bar, and I said that's the loop counting parameter. So local divergences, well, the one loop local divergence will appear suppressed by extra one loop factors, like this. So, as a result, so what's the proof of this? Okay, the local divergence of one loop diagrams made from S classical. Okay. So what we're saying is that this is the divergence coming from one loop diagrams if you never heard of this and just use this in your action or in your path network. And the reason is that this just subtracts the divergence. Okay? And the proof because there's just ever so slightly one observation you have to make, is that to order h bar, which is to say one loop order, where in the effective action I think of this as h bar to the 0. Okay? To order h bar in this calculation of the effective action, we must do one loop diagrams using S classical vertices and propagators, and tree diagrams so this is to calculate gamma phi. We have to use tree diagrams made with S local so we're working to such a low order when we calculate one loop diagrams that we can use either the tree level diagrams here, the vertices from here, and the process of forming a loop introduces an h bar, as we've already gone through, or there's already an h bar in front of every term in this, which means we can't afford to use it in a loop diagram. So it just contributes the way it is to the effective action. Note, the effective action is of the same species as the action itself. It's got the same argument. And in fact, the leading order approximation to the effective action is just this. Okay? It's just the classical action. So this is the thing that, again, I can say it 5 different ways, but you should just play around with it because it's so simple. We are then saying that, therefore, gamma phi nu, okay, is going to equal gamma phi old made hopefully from and then minus this h bar and this itself is equal to its classical approximation as classical phi plus these kind of diagrams, okay, where this vertex and propagator come from S classical phi. Okay, so this will be h bar to the 0, this will be sort of order h bar to the 1, and this is already h bar to the 1, so I can't afford to make loops out of it, but I can make it go for the ride just like this, and that's it. But because it looks like this is simply subtracting the divergences encountered here, hence there are no divergences, and we get this result. Okay? And this is what we'll call the renormalized okay? This action here is often the result of doing this. It looks like a very active statement, and it's called subtraction. For obvious reasons. And it seems to render our old divergent effective action, naively the divergent effective action, is now rendered finite by the process of subtraction. Okay. And as I said, I want to explain to you why the process of subtraction should not be viewed as a process, but merely an observation. Right now, it seems like I've changed the theory by subtracting, by changing the action used in the path integral by doing this. But we'll see that that is sort of really a passive move. So play around with it till you see, I mean, if it's not immediately clear right now, why it is merely subtraction. Okay. This thing just appears as an add-on to everything going on. This is local divergence. That's the kind of local divergences of this. Okay, how does this generalize to arbitrary loops? So the key here to saying that this is a same kind of species as this, namely a local action. Maybe I should do that first. Yeah, sorry. I don't like this word subtraction, as I said, because it sounds like you're meddling with the theory in some new way, rather than just noticing that everything is good, and there's no problem at all, okay? So I'd like to give that viewpoint first, and then we'll talk about the generalization to higher order. So, subtraction looks like an active, but it's really a passive observation. So consider, for example, phi to the fourth. So the action in path integral or the equivalent Hamiltonian is S, and it's usually called the bare action. Okay? So this is called the bare field, and this is called the bare mass, and the bare coupling. And the thing about the bare thing is it's all that there is. Everything else is just an observation about this. But this bare action is the guy that's driving the path integral. So there's no, just do the path integral, throw in some cutoff, and that's it. So you make sense of the path integral by having an ultraviolet cutoff, and here's the action, and that's it. Okay, just shut up and calculate. That's what we're supposed to do. But we're going to make an observation that this action can be decomposed. So sometimes it's also written as S naught. That this thing can be decomposed as an SR, or renormalized, plus an S counter, it's called counter term, here we're just making this separation. As I said, it's a passive group. And S renormalized has a kind of self-similar form to this bare action, but with a renormalized field, a renormalized mass, and a renormalized coupling. I'm going to put brackets, parentheses around these to say that in practice, so that it's kind of the default is that if you don't bother to write that subscript R, that you're talking about the renormalized field, the renormalized mass parameter, and the renormalized coupling. Okay, right now I'm emphasizing its existence by explicitly writing the R. Okay. So maybe and this S counterterm also has a very similar form, which is similar. So it's being written in terms of this default renormalized field in this way. Okay. This is a kind of way of making apparent something. This is a way of doing bookkeeping for an observation. The observation could be made just at this level without ever having invoked this stuff here. It's just for purely human convenience and absolutely no, other purpose, shall we say. Okay, but we're human, so something. So here it is. So what is this relationship between these three things? Well, it's easy. So this phi there is equal to root 1 plus delta z. Of course, all I'm doing is comparing the sum of these two and these and matching it up, obviously. So you can check me. This is equal to this. Okay, if I'm equating these actions. And this is often called it's just called z. Okay? So the bare phi is merely a wave function renormalization of the renormalized phi. Okay? And hopefully this brings to mind things that you've seen when we studied the effective, the self-energy. Okay? When we studied self-energy, we came through this kind of action, but we want to see what's the systematics of it. Delta m squared is z m naught squared minus m squared. And delta lambda is equal to lambda naught. Okay. Other than the fact, they're the irritating z factors, but other than that, it's sort of, if in fact the renormalized field and the bare field were the same, all you're saying is that I'm splitting up my bare mass into a renormalized mass plus a extra correction. Okay? And the same with the coupling. And you can see the idea is to try and track this thing here. That the delta m squareds are going to, the delta parameters are sort of capturing what could be sitting in here. The structure of local divergences, since they're local, I can name them as a kind of So the renormalized parameters are somehow here, and then there's a kick that we're giving the action. And the kick is given by these delta parameters. Okay. In all the possible local divergent structures that you can imagine. Now at the moment, I'm just writing up to phi to the fourth, but we'll discuss the generalities. Yeah.
There are R's on the m squared and the lambda.
Yes, you see, I've already started dropping them. But you were wrong.
There's a 4 factorial on the top.
There's a 4 factorial on the top. The nice thing about the effective action, I don't think Peskin is doing it this way completely, I mean, right from the start. But the nice thing about the effective action approach to thinking about renormalization is because of the similarity of the loop level diagrams. They're in the same, they sit inside what they call the effective action, which is a species of object similar to the action. A lot of these factors go for the ride in similar ways. Okay? So it's a little more forgiving, which is why I like. Okay, so this separation, you see, it's a little bit arbitrary. I always have one set of input parameters, and this separation into two sets seems a little bit arbitrary, and it in fact is a little bit arbitrary. But what's the thinking? Let's ask, why do we make this separation? Can't do it. Stuck. Okay. Okay, so the strategy is very simple, is at every loop order, right now you can just think about one loop order, right? But at every loop order, we choose the delta z, the delta m squared, the delta lambda, to subtract, in the technical sense, to subtract new local divergences arising from loop diagrams for gamma made from this plus S counter term So here's the idea. Even though secretly we know that all of this is just a separation, seemingly at least partially arbitrary. So right now it seems like a totally arbitrary separation where every quantity, every bare quantity is just the sum of a renormalized quantity and a delta. And that separation seems so arbitrary, okay? But now I'm going to restrict the delta. How? First, I'm going to use the sum of this and this, namely this. I'm going to use it to calculate Feynman diagrams contributing to some loop level effective action. whatever this is and this is, I just use it, I add the two, and I calculate contribution to some effective action. Then I discover that there are local divergences. So what I do is I modify these deltas to subtract off those local divergences. Okay. Now suppose I've already done this to some order. I've worked to order h bar to the 17th. And I've got this, and they are working in beautiful concert. That is, these deltas are correlated with these m's in just the way that the sum of the two subtracts off all the divergences that you'd ever get up to order h bar to the 17th. Then I do one more loop, h bar to the 18th. And now I suddenly find some new ultraviolet divergences. But they're local, okay? Then I choose the order h bar to the 18th value of delta z, delta m squared, and delta lambda to subtract off those, okay? To subtract off the order h bar to the 18th ultraviolet divergences. And you might say, but wait, those new deltas, when you stuff them into loops, are going to give me even newer ultraviolet. But they're not going to that's not going to happen at order h bar to the 18th, because these are the corrected deltas here are already order h bar to the 18th. So it's just like this. If this was order h bar to the 17th, this is order h bar to the 17th, and you already have something like this up to order h bar to the 17th. This is already finite. By some magic, you've already made this finite. And then you calculate order h bar to the 18th, which means that some of these order h bar to the 17th counterterms can appear in loops. And then, of course, there are all the 18 loop diagrams you can draw, starting from even the classical action, the renormalized action. You get order h bar to the 18th ultraviolet divergences, and now you can subtract that with an order h bar to the 18th correction to this S counterterm. Okay. But this itself will be only contributing at tree level because it's already order h bar to the 18th. Okay, it's a generalization of this other. Okay. So let me see if I can. So the strategy is this, and to try and write that out a little bit, we write to do this. We write so whatever order in loop counting you want to go, however high, I'm not going to write that, okay, formally infinity. However much perturbation theory you want to do, you start putting in these counterterms, and there's like a one loop, n equals 1, one loop counterterm action, a two loop counterterm action, a three loop counterterm action. You write it like this. If you want to so then the strategy is compute gamma, and similarly, we write gamma of phi is equal to, well, the tree level approximation is this. Y, let's just check. Counterterms start at order h bar to the 1. Okay? So if I want to write the h bar to the 0 approximation to the effective action, it's just that guy. Because this is, I'm saying, every term here, as you are going to see, the algorithm is going to give all of these terms to the order h bar, the first, second, third, And then there's going to be order h bar to the 1, gamma, these are exactly the story I just that I had previously done. Right? One loop. This means one loop diagrams made out of this and adding this. You're not making loop diagrams out of it. You're just adding this because it begins at order h bar to the 1. So I can't afford to stuff this into any loops. And so I get this, and this is finite. Why? Because I've chosen. So this is finite by choice of S counter term 1. Okay? I choose my delta parameters to subtract the local divergence that comes from calculating this at one loop using the vertices of S renormalized. But then there's h bar squared terms where I calculate the order h bar squared, I calculate the two loop effective action. And this thing is, so this thing is diagrams made, so two loop diagrams made from S renormalized vertices plus one loop diagrams made with one insertion of S counter term in other words, here is a diagram where this is a, if you can think of even a 2-point thing as a kind of a funny vertex, this delta z. Here is this is order h bar squared because it's one loop. But this delta z is also got an h bar in front of it. Okay. Another example would be this, where I'll put a circle around this to say this is delta lambda and this is lambda r. This is again order h bar squared. Because this delta lambda is order h bar, if it comes out of S counter term 1. And then I'm doing a one loop diagram which always introduces an extra h bar. In fact, you can see it. The h bar is secretly just the power of lambda. And so it's order h bar squared. So this thing, when I calculate them all these ways, I'm going to hit some new ultraviolet divergences, which are formally order h bar squared. But I'm going to make this finite. How? By cleverly choosing, by choice of S counter term 2. Because this thing contains honest two-loop diagrams, like here's a two-loop diagram that sits inside gamma. You amputate the legs and so on. It contains one-loop diagrams, which are, however, order two-loop, because they contain one-loop counterterms that were introduced to make the one-loop effective action finite. And then it contains tree diagrams which is also order. So maybe I'll put a 1 there. because this delta lambda with a 2 comes out of this guy. It's formally order h bar squared. And so there are 3 types of diagrams that sit in gamma 2. Honest 2-loop diagrams, 1-loop diagrams with insertions of 1-loop counterterms, and then tree diagrams, or tree vertices, since you amputate, there's not much to do, which come where every vertex is already formally 2-loop order, and so you don't make any more loopy diagrams out of them. But the sum of all of these. Now this last guy is just an add-on, because there's nothing to calculate here. Since you're amputating, the vertices, the action itself is just added to the effective action. Or if you want, it's a kind of way of subtracting. So this is chosen, all of these guys are chosen to subtract any divergences appearing in any of the loops that you encounter. The fact that that all divergences are local means that I can just use these local types of things to put minus the divergence here, here, and here incurred from gamma, and it'll just subtract off the divergences. Okay? And so on. Every loop order will choose the delta z at that loop order to subtract off any new local divergences arising at that new loop order made from diagrams out of this and any lower order counterterms. This is an example of a lower order counterterm appearing in a loop contributing to the order that I am now talking about. So this is the algorithm. Let me see if let me explain one thing first, which is why is this? So it still seems like it is sort of an active operation. Okay, I still have I've not managed to explain that it is truly passive. But whether it's active or passive, I want to say that one thing is already okay. You see, I don't care if it's active or passive, who cares? I really care that I have Lorentz invariance and quantum mechanical unitarity. Okay, that's all I care about. Let's first make sure that that is at least true. By the way, this is in some sense telling you the strategy, and there are some questions hanging out, which is, why are these the only local divergences? Yes, I agree, these are local. Why are they the only local types of divergences? How do you know that just these things are enough to subtract all divergences? There may be other local things you could have written down, like phi to the 6th. Why didn't you write that? So that's a hanging question. Hold it. Hold it. But and there are other things, which is this is a strategy, but will there be some obstruction coming at multi-loops and so on? We've seen how it works at one loop, but what will happen at higher loops? Will it really go through in this way? But I wanted to at least say, if this strategy goes through, why should we be happy? Whether or not we have an active or passive story here, why should we be happy? But yeah.
I missed when you were giving examples for the order of H-bar correction to the renormalized effective action. That contains one loop contributions from the renormalized action and propagators from the counter term.
The propagators should be treated. So, for example here, this is an example where you should think of this as drawing the usual propagator like that, and another one here And here you're inserting, you're thinking of this as a kind of a rather weird vertex. It's not a 3-point vertex, it's a 2-point vertex. And as a 2-point vertex, the Feynman rule for it would be the, so it would really be a minus I, the d mu's, when you Fourier transform to get the momentum space Feynman rules, would turn into a p squared. I think it may be a minus p squared, so, and then this delta z. So as a kind of a Feynman rule, you insert, you're working strictly to one loop order. I mean to two loop order. So you're doing a whole loop, so that's already one loop used up. And then you're going to take the one loop guy here. So you don't resum it in any way or anything like that, just one loop and that's it. And so what you shouldn't think of this as a whole propagator. You should think of it as one naive propagator, plug in this, and then another propagator. That's an example of a diagram. Of course, you could write all possible diagrams of this order that you can. Okay, so why are we supposed to be happy if this strategy proves to be possible? We can keep doing this. If at every order I can modify the counter term at that order by h bar to whatever order I'm working in. I can keep on modifying it to subtract out the divergences. Then why should I be happy? So if this strategy succeeds, then to any loop order we have gamma phi, and hence W of j, since that's just made out of tree diagrams using these effective vertices, or the S matrix, if you want to go all the way to some experimental observable. We have all of these things, okay, basically the diagrams, insensitive to the UV cutoff. Because every time we have sensitivity, we have introduced counterterms carrying the opposite sign, but the same sensitivity, to subtract off the sensitive terms in gamma. Okay? So all we're left with is a gamma which is insensitive to the UV cutoff, which we can therefore take to infinity. And then you see, whatever cutoff procedure you have is always introducing something unphysical. With Pauli-Villar's cutoff, you break the spin statistics connection. If you have energy enough to produce these Pauli-Villar's particles, they would be unphysical because they would violate the spin statistics connection. If you use a lattice, space-time lattice, if you go to high enough energies that you are probing the lattice length scale, then suddenly you're breaking the Lorentz invariance that you took as axiomatic. You decided Lorentz invariance was what you wanted. So whatever cutoff you use, we call it a cutoff or a regulator because we don't actually believe that particular structure. If it was something which played by every rule, Lorentz invariance and probability conservation and so on, we don't have to call it a cutoff. We could call it a possible new physics. Okay? So, but we have removed the sensitivity to the ultraviolet cutoff. So by taking the cutoff to infinity, and thereby removed any unphysical feature of the cutoff. Furthermore, secretly, we are just using some S naught. Secretly, this process of splitting it up and so on, well, you can just say the sum of this and this is some particular choice of S naught, which is a local action which corresponds to some local Hamiltonian with the standard, so some corresponding to some Hamiltonian, and therefore unitary up to the cutoff. So we are doing Feynman rules from this action, which we know by the derivation of the path integral corresponds to just doing perturbation theory of a perfectly sane Hamiltonian, okay? We're secretly just doing this. Time evolution. It's perfectly unitary, it's perfectly good. Well, it was almost good, except that we had this damn cutoff, okay, that we had to introduce. But on the other hand, I've removed the cutoff. The cutoff has now been taken to infinity. So then we're good. Okay. One way to think Pauli-Villars is very useful. It's all good quantum mechanics, except it violates the spin statistics theorem. But that will only catch up to you if you have the energy to produce the Pauli-Villars particles on shell. But if I'm removing the mass of the Pauli-Villars particles to infinity, I will never be able to, I'll never have an experiment that can produce Pauli-Villars particles on shell. Hence, it's perfectly Lorentz invariant and unitary. That's it. So this is the sense of satisfaction you're already supposed to get. That is just this. And
I have one question.
yeah.
So technically, we have worked in terms of separated actions, so renormalized actions and counter terms.
Yep.
And the fact that we have good unitarity means that the Hamiltonian corresponding to the action will be Hermitian.
Yep.
Now, order by order, if we work in this language,
Yep.
then say at n loop order, let's say I designed the counter term such that I achieve it that way. But how do we know that the Hamiltonian corresponding to that language is still Hermitian, so that I have good unitarity at that?
So, in the end, other than having carefully chosen the coupling constants, so for example, when you write the Hamiltonian, when you write a Hamiltonian like this, and you know, just think of what these phi's are. It's the usual kind of harmonic oscillator-like operators, right? When you write something like this, it's clearly a Hermitian operator, so it's clearly a good Hamiltonian. Now, is it bad Hamiltonian for some particular choice of lambda? For example, if I write this lambda, let me call it lambda naught. If I write this lambda naught as some particular lambda plus some other particular lambda, does the fact that this has been carefully coordinated with this change the fact that this is still nice Hermitian Hamiltonian? No. I've only specialized by saying that this lambda naught is this plus, and this delta lambda has been carefully coordinated with this to give me something finite. But I would say that when we wrote Hamiltonians like this and we were happy with them as being at least Hermitian, we were happy for any value of these couplings. And the only problem was that in detail, when you worked out perturbation theory, you found that you were hitting divergences. Now we're saying, no, actually, I haven't yet hit this passive word yet, but let me say it the way we're doing it. That by some miracle, which will only understand when we understand the passivity of this. But by some miracle, by choosing lambda naught to be very special, I even have finiteness. Then I would say you have both. You have the hermeticity that is formally there up to ultraviolet divergences. Then you don't even have the ultraviolet divergences, so what more did you want? Right. So that's the way you should view it for the moment. Okay, so let me get the passive part out. What can I afford for this? So the passive part. So the bare parameters and the cutoff, whatever your cutoff is, high energy cutoff, to doing going to finite correlators or finite gamma in terms of the parameters of the renormalized action, you are calculating this gamma. Okay? And you might say, no, I'm not calculating. It's not a function of just these. It's a function of these and these deltas. I need to specify these and I need to specify these. But with the delta, with all these guys, determine by so as to ensure finiteness. So, really, are these deltas independent parameters? No, they're strongly constrained by this requirement that I get a finite answer. Once you tell me these guys, I'm supposed to calculate diagrams, and in every loop order, I'm actually choosing these guys to subtract the divergences incurred by this choice of parameters. So in that sense, we're thinking of it as sort of the delta parameters. So we're thinking of S counter term as okay, so let me try and now say why this is, however, just a passive thing we're doing. So let's choose two physical predictions. Say A, I'm about to slough over, I'm about to pretend that the irritating thing called wave function or normalization does not exist, and then I'll come back to talk about it. Okay? So So then you can say, oh, well, so in fact here, there are just these two parameters, it's m and lambda. Okay. So let's just consider two physical predictions, and they're completely determined by these renormalized parameters and b. So choose two physical predictions, two things that you can actually go out and measure. And because of this algorithm that we have, everything can be computed by just telling me these guys. And I will make things finite by choosing these counterterms to subtract out the divergences incurred at lower orders. Okay. So choose two physical parameters like this. And invert the relation so that we have if you can calculate in finite, as a finite function of these guys, you can calculate two things that you can actually see, go out and measure. Then this two measurables and these two renormalized parameters, let's invert the relationship so that it looks like this. Okay? But that means, in this way, all predictions or measurements C so of course anything I can in this, once I've done this renormalization procedure, any question I ask I can calculate in terms of these renormalized parameters. But then I can stuff in for mr squared and lambda r these two functions, and I end up with something that looks like this. So all measurements, all things that you can measure, can be predicted in terms of these two measurements. You go make these two measurements, and then you can calculate everything else, where this is, of course, C of mr squared A and B. Lambda r A and B. Okay. But what this says is that this whole procedure of separating out into mr squared, into the renormalized thing, the deltas, all of that, you've done away with it. What you're observing is that indeed, so indeed, all measurements, measurables, C, are UV sensitive, or at least most of them, or without proof, any of them could be UV sensitive functions C of the bare parameters. Yes, if you just go and compute, this is the only path integral that we're using. We're using a path integral made from this action. Whether I decide to write this like this plus this or not, it's this action that I'm using. If you calculate, you will find that they are functions of these bare parameters, and they are very sensitive functions of the cutoff. But they are equal to but they are, but you can, instead of writing them in terms of these guys, you can write it in terms of these parameters, and then you're insensitive to the cutoff.